All right. Sorry. All right, starting the stream. Let me see. Is it working? Is my stream working? Chat. How good is my audio right now? Okay, the audio is pretty good. The audio is actually pretty good. All right, cool. So, well, it's time to do homework. After I share the links. Give me a sec. Okay, so today I'll be doing. Actually, I should bring the question up here immediately so you guys can look at it and see how it goes, see how to solve it. While I'm posting my links everywhere. This is gonna be. Alright, this is gonna be our question. Alright, and now I'm gonna be posting the links. Give me a sec, guys. Hi. Hello. Welcome to the stream. Welcome to the stream. Okay. Alright. Let me just copy and paste that. Almost forgot to tweet about it. How do I find my stream's link again? There it is. Click, and then do I copy that link? Please let me copy the link. Thank you. There we go. And then just post this on Twitter. Boop. More homework. Okay, finishing my homework today since silksong, so I can play silksong tomorrow. Boom. And post. Alright. And how are you guys doing? How many of you are in chat right now? One. Hello, one person. Is it you? Redump. Welcome to the stream. Alright, and now I paste this link everywhere again. On Discord now, this time. Going there. Boop. Post that link there. Yes, hello. Thank you for joining in. Let's get almost started. Just in a bit. Hold on. I have to self-promote. I need views. It's just Discord is taking a while to load, so it's taking me a bit of time to paste the links in the chat. It's probably taking this time to load because like I'm live streaming. It takes quite a bit of a resource on my computer. All right, I think that's gonna be enough. Feels kind of like private tutoring session right now. Honestly, true. There's only one person here. I'm gonna watch the stream on my phone as well, so I can read chat from my phone. Because I don't know how to make it show up. I don't know how to make chat show up on my computer screen. So I'll be reading my chat on my phone. Alright. As usual. So let's get started. The first question is one sec. My phone is not working. Now my phone is working. Okay, cool. Now I can read chat. So, first question. I'm gonna be speed running through this because tomorrow, silksong is tomorrow. Yay. Silksong is tomorrow. Am I drawing her right? I think that's not right. Yeah. Silksong tomorrow. That's very much not right. Something seems off. I think I made these too long. Anyway, Silksong tomorrow. I have to finish my homework today, so I can play it without caring about my homework not being finished. So let's do it. All right. First question. Consider a small frictionless puck perched at the top of a fixed sphere of radius r. If the puck is given a tiny nudge, so it begins to slide down, through what vertical height will it descend before it leaves the surface of the sphere? Hint: use conservation of energy. This is actually a this question is actually used in an Olympiad for physics. In Thailand, it's called the TPH. Actually, no. In Thailand, we typically go through the POSN camps. I don't remember what it's abbreviated from, but basically, it's like the camp to select kids to go to the Olympiad, Olympiads for physics. And then there are 2 camps, and then after you pass the 2 camps, you get to go to TPHO, Thailand Physics Olympiad, in which I won a gold medal in subtle flex. And then and this question is actually in the first camp, which is pretty crazy because this is a high school, middle school to high school level of physics, and they're telling us to use university level. It's a university level question, so that's fun. Consider a small frictionless puck perched at the top of a fixed sphere of radius r. If the puck is given a tiny notch, which means it's basically saying that the initial velocity is 0. Let me check the audio first as I'm streaming. I want to make sure that my audio sounds tolerable. Give me a sec. Okay, is it working? Okay, it is. It's actually kind of good. It's good. I guess there's the fan noise, which is a little loud, so I'm gonna go ahead and turn the fan away from me real quick, which means I'm gonna be in a bit of heat, but I think it's all right. The audio is fine. Thank you. All right. So, if the puck is given a tiny notch so that it begins to slide down, through what vertical height will it descend before it leaves the surface of the sphere? The fan is tolerable. All right. So here, let's say that we're gonna assume that this puck is gonna leave the sphere at this point. Give me a sec. Let me draw that. I'm bad at drawing. I'm gonna say that it's gonna leave the surface of the sphere at this point. By leaving, it means it's no longer in contact with the sphere. And then I draw this, and I'm gonna say that this point is theta naught, I guess. So here, it means that give me a sec, let me drink some water. It means that at this point, the object is no longer touching the surface of the sphere. But when the object is not touching the surface of the sphere, let me write this out real quick. Let me draw the free body diagram real quick. It's from this point, but like I'm gonna draw it from. I'm gonna like make it perpendicular. So here, the force pulling it into the center of the sphere, the force is going to be mg. Is it sine? It's not sine. It's cosine theta, right? It is cosine, yeah. Mg cosine theta. Theta naught at this exact point. And at this exact point, the surface of the sphere is also pushing the object, the puck, with the force n, right? So over here we have mg cos theta naught, and this is going to be n. So we can write the equation that the acceleration is going to be equal to the total force. So we can write that the acceleration is going to be n minus mg cos theta naught. And in the case of a circular motion, the acceleration should be negative mv squared over r for circular motion. All right. Yeah, for circular motion, the acceleration is going to be negative mv squared over r, which means it's pulling it inwards so that it would remain in a circle. So this is the equation that we have set up. Now the question is, what is the question? One sec. Through what vertical height will it descend before it leaves the surface of the sphere? Which means that it's asking for this length, which is equal to r. This is the length r. This is going to be length of r cos theta naught. So this length here is going to be r times 1 minus cos theta naught. All right. So the question is asking for this one. So we have to find theta naught, which angle at which this object will slide down and then fall off. So the object is going to be like standing like right here, and then it's going to fall, and then it's going to slide off. By sliding off, it means that it's going to jump. It's no longer going to be pulled in here. It's just going to go off like that. Yeah. All right. So let's see. When it stops touching the surface of the sphere, right? What happens? What happens is that the normal force n here is 0. When it's not touching the sphere. So that means at theta naught, mg cos theta naught is equal to mv squared over r, negative mv squared over r, which we can then solve the equation, which gives us the fact that r here is just big R, right? Which gives us g cos theta, cos theta naught equals to v squared over gr. So we have found theta naught, but not exactly, because we don't really know what's the velocity over here just yet. But we can find it by using conservation of energy. Over here, actually, wait, hold on. Can I play music? Okay, can I play music? What music can I play actually? Because it's a little bit it's a little low. Wait. YouTube.com. What music can I play? Classical music. You know what? You guys can request non-copyrighted music in chat, I guess, and I'll see if it's copyrighted or not, and I can probably play it. So we also know from conservation of energy that 1/2 mv squared plus mgh is constant. In this case, it is constant because there is no friction. So if there is friction, it's not going to be constant. There's going to be a little bit of dissipation, but in this case it is. So let's see. mgh here, initially, I'm going to write out both at the end and at the start. Initially, what we have is we have v equals 0. and we have h here is going to be equal to r at the start, which means that is when the object was sitting right over here. And then once the object has slided down all the way down here, it's going to have some velocity, obviously, and that velocity is going to be 1, and that velocity I'm just going to call it v. But now it's no longer. The height is no longer just r. It's going to be r cos theta naught. It's going to be r cos theta naught. So now we can write this as mgr cos theta naught. Boop, boop. And now we can find v squared. So let me just move. I can cancel out the m's. I can also write that v squared is equal to 2gr times 1 minus cos theta naught. And what we want isn't theta naught. The question asks us for the vertical height that it descends. So the question asks us for this one, which is r times 1 minus cos theta naught. So what we want to find is we want to find this guy right here. Which isn't a problem either, because we already know what v squared is, right? Wait, would it be a problem? No, not really. I mean, we can literally just plug that in. We can find theta naught first. Fine. We'll find theta naught first. So now we know that this is going to be equal to gr cos theta naught from this equation over here. From this equation we got earlier over here. And so now we can cancel out the g and r. So now we know that cos theta naught is equal to 2 minus 2 cos theta naught, which means cos theta naught is equal to 2 over 3. And what we wanted to find was r times 1 minus cos theta naught. Therefore, the answer (1 minus cos theta naught) is equal to r times 1 minus 2 over 3 equals to r over 3. And that is our answer to the first question. Nice. Absolutely. So, yeah, this question is fairly simple. You have to but you have to be able to identify what exactly to do. I've seen this question like 10 times before. I've taught my brother how to solve this question, so I was able to do it fairly quickly. But I'm not expecting the same for the next question. What's the next question? Wait. The next question is 4.23 in John R. Taylor's book. 4.23. Which of the following forces is conservative? Casual flex. Yeah. Yep. Flexing. Oh shit, wait. Okay, whatever. Okay, and I mistyped a little bit, so you might be able to see that this page is actually a little bit shorter than the other page. I mistyped a little bit, but it probably doesn't matter that much. So let's see. Which of the following forces is conservative? Yeah. Okay. Which of the following forces is conservative? What does it mean for a force to be conservative? Well, you see, a force is conservative when it's when it can be written in terms of potential. That is, when the force is conservative, it means that the force can be written as a minus gradient of potential energy. So, for example, gravitational force is conservative because F equals to negative gmm over r squared, right? And potential energy U is equal to negative gmm over r. Here you can write out the fact that F equals to negative gradient U. Now what this means is that if it's conservative, then it conserves energy, as its name implies. And the way for the force to be conservative is the condition for conservative force for conservative force is that the curl of the force is equal to 0. This is the condition for a force to be conservative. This is because you can prove this because of the fact that between 2 points, a force has to be conservative if you can go from here. If you go from here to here or here to here, and regardless of path, you have the work done in both paths is going to be equal. You know, work equals to F dot S, right? Work equals F dot S. No matter which path you take, work here has to be equal for the force to be conservative. And it's going to be, and therefore, if it's not equal, what happens? If it's not equal, then you can then it means that going from here, walking over here, you're gonna get work equals to you're gonna get work equal to something. And if you walk backwards through this path, the total work is gonna be 0. If it's conservative, the total work is gonna be 0. But if it's not conservative, then walking along here and then walking back here, there's gonna be some work being done. So, and you can and then if you add them up, if you add up the entire area, it means that you're integrating the curl of this. You're integrating the curl of this shape. Whatever it really means. What the bottom line is, if you use the gradient vector, if you use the gradient operator, the Nabla operator, which is equal to partial derivative with respect to x plus partial derivative with respect to y plus partial derivative with respect to z, and then you apply, and then you cross. This is technically a vector. It's an operator that is a vector because it has vector components in it. So if you can cross this with some vector field, and you're going to get another vector field. If that vector field is called the curl of F. If that vector field turns out to be 0 everywhere, then F is a conservative force. So let's just go ahead and do that. Let's look at the first one. A. F equals to K X 2Y 3Z. And yeah, this is the force field. So now we use the curl operator on F, and we're gonna get we can factor out the K. What we're gonna get is the first component is gonna be dy by dz of the second term. Well, wait. Yeah, okay. So there's gonna be this term, but okay, wait. How do I explain this? You know what? I'm just gonna write the components out. Okay, so the first term, this one is the x component of the resulting vector. You can see that there is no x mentioned within the x component. It's just y and z. And it's a cyclic permutation. So over here, it would actually be, I think it's going to be fx by z. minus f c by f by x, and this one is going to be f what is this one? This one is going to be y by x subtracted by not c. What the fuck am I saying? Fx by y. Whoop. And this is the curl for any arbitrary vector field. All right. So let's test that out on this one. So the curl for this one is going to be equal to what? Derivative of the c component with respect to y is equal to 0. So this one becomes 0. Derivative of y with respect to c is 0 as well. So this first term is just 0. Derivative of f of x with respect to c is also 0. Derivative of the z-axis with respect to x is 0. So it's basically 0 everywhere. Therefore, f is conservative. Then we have to find the potential. We know that f is equal to negative gradient of u, and we have to find the value of u. Here it's actually fairly simple, I think, because we can just integrate it, and we're gonna get u is gonna be should be something like negative kx, negative 1/2 kx squared minus ky squared minus 3/2 c squared. I think that's right. Yeah, I think that's correct. Yeah, we can verify it. And of course, there's plus some constant. It's the constant is arbitrary. Let's see. Negative gradient of u is going to be equal to negative of, we take the derivative with respect to x first, so we're going to have kx, negative kx, because you take the derivative of this term. The partial derivative, the rest goes to 0 because it doesn't depend on x. And that's in the x-axis. And then you take the derivative with respect to y, and then put that as the y component of the vector. And this does line up with our force, and the same applies to this one. So this is going to be minus 3 kc. Kc is the axis, which is equal to force. So that is that is the question A. So question B, we do pretty much the exact same thing. Y x 0. Okay. For question B, f equals to y x 0. So that means the curl of this vector field is equal to, we just use this exact same formula for curls. So first of all, the c component is 0. So this component over here is 0 because there's no c. F of x here is y, but it's just y, doesn't depend on c, so this term becomes 0. Fc is just 0, and it doesn't depend on x, so that term is also 0. So this middle term is 0. And so on to the next term, we have derivative of y with respect to x, derivative of the y component, which is x, with respect to x. So this one should be 0, it should be 1. And you subtract it by fxy, which is going to be 1, which is going to be 1 as well. which is equal to the 0 vector. Therefore, this force is also conservative, which is actually a little surprised. I'm actually a little surprised. I don't know how this graph would look actually. Let's see how this graph look if it's if the y values if the y value is high and x is 0, it means that it's going to be the vector is going to be pointing right. If the value is lower, it's going to be like going a little less to the right. If it's going if y is negative, then it should be going negative like that, which is odd because that means that in the middle the curve shouldn't be 0 unless I'm missing something, and that is because I am, because along this field line I'm pretty sure it's gonna look like that, which means that it's like which means this this force is gonna look something like this force should look something kind of like that. Boop, boop, boop. The force is going to look something like that. If a particle is over here, this force is going to be pushing it along this line, along that line. Okay. Yeah, that makes sense. So let's find the potential for this force. The gradient of u is going to be equal to negative f. So that means partial derivative with respect to x along the x-axis of u plus y-axis u with respect to y, z-axis the u with respect to c. It's going to be equal to negative f, so it's going to be equal to negative k y x 0. And now we can indeed find it by integrating. We know that this we can just say that u is equal to negative kxy. I think that works. Let me drink some water real quick. I'm actually getting a little hungry, even though I've only started like half an hour ago. I should have brought some snacks up here. Let's see, we take the derivative with respect to x. We do get the force. We do get the correct force, yeah. If we take the derivative with respect to y, we get the correct force. So yeah, this is our answer for question B. You can take the derivative and verify the answer. And the last one is negative y, x, and 0. In this case, it's just the same thing. Almost the same thing. We have to find the curl of f. And f here is equal to, you know what, in fact, I'm going to select this entire thing. I did not select that, right? This is not an iPad. Fun fact, I don't use an iPad to like take my notes. I straight up use my notebooks. Like, I don't know if this is the case for everyone's university, but like at university, they've been using like the iPad and a tablet to like write stuff. But I don't use it because we only have one. Well, not just that, but I'm also like, I like writing it in paper better. But here, as you can see, before this one becomes 1 minus 1 because the last component here was y. So it becomes, so this derivative is 1, this derivative becomes 1, subtract them, it becomes 0. But in our case, this term is no longer just y, this term is going to be negative y, which means you take the derivative and you're going to get negative 1. You subtract them, you're going to get plus 1 instead, so the total becomes 2. Therefore, f is not conservative. In fact, how it looks is this vector field is actually going to look something like it's gonna look kind of like a, actually not in that direction, I think. Yeah, no, it's not in that direction. The vector field is gonna look something like a curly, or like a spiral. So this is how the force looks like, and it's not conservative. This is not a conservative force. It's gonna change energy. Like it doesn't. If this force is applied, it doesn't use. You can't express it in terms of potential energy. Yeah. All right. So that's that. That's the next question. So on to the last question for classical mechanics. We're doing we have a pretty good timing today. It's only been like what, half an hour, and we're almost done with the first. Subject. Although the next subjects are gonna be a little bit of a pain. Yeah. Let's see. What's the next question? The next question is 4.34 in Taylor's book. So let me create a new page for that, and then I'm gonna go screen cap the question. Let's see, 4.34. Okay. What do we have here? Ooh, boy. Let's see. Lengthy problem. Alright, maybe this is the one that's gonna make my stream a little longer than I had anticipated. You know, my computer is dropped. My frame is dropping a little bit. I'm gonna enable performance mode on my OBS Streamlabs. I'm not using OBS to stream. I typically use OBS to record, but now I use OBS Streamlabs to, stream. I feel like it's more convenient that way. Sorry. Alright, an interesting one-dimensional system is a simple pendulum consisting of point mass m fixed to the end of a massless rod of length L. Whose other end is pivoted from the ceiling to let it swing freely in a vertical plane, as shown in figure 4.26, which is not this one because it's in a. I didn't screenshot that, but you know how a pendulum looks. I'm pretty sure. You guys know how a pendulum looks. It's getting a little hot in here. I'm gonna go face the fan towards me, but the noise is gonna go up a little bit, so please don't mind me. All right, so pendulum. It's gonna look like that. Let's see. What's the question here? Prove that the pendulum's potential energy, measured from the equilibrium level, is that. Okay. The pendulum's position can be specified by its angle from the equilibrium position. Could also be specified by distance s, but the angle is more convenient, yeah. Alright, so part A is easy enough. Wait, then what the fuck is this question about? What the fuck is this? Oh, this is for problem 3.4.36. Okay, this so this is just clickbait. Alright, we can delete that. Okay, let's see. The pendulum's position can be determined by angle. So, okay. The pendulum's position can be specified by its angle from phi from its equilibrium position. So we draw that out, and this is our angle phi. I shouldn't write that over there. I should write over here, and then write L over here. Whoa, hello, welcome to the stream, Tasty. Yeah, we're doing more physics homework, and we're doing a lot of physics homework because I'm clearing up I'm gonna clear up as much homework as I can because silksong is tomorrow. So I would have time to play it without, worrying about anything. So the potential energy at equilibrium position V equals 0, silksong tomorrow, absolutely. We set U equals 0 at the equilibrium position. Wait, let me. Over here we set U equals 0. We also know that gravitational potential energy on the smaller scale, on the non-relativistic and on the non-relativistic and the in the small scale is mgh, as we know. So the question is how tall is this? This is the value of h. How tall is this in as a function of phi and L? Well, it's kind of easy because this whole length here is L. This whole length here is L, so I'm going to write that at first. The whole length here is L, and the length over here is L cos phi. Therefore, h is equal to L minus L cos phi. Simple. And therefore, this is the gravitational potential energy of the system. Yay! Yeah, this one A is kind of easy. Next up is show that by differentiating your expression for E energy with respect to time, you can get the equation of motion for a phi, and that equation of motion is just a familiar torque is equal to the moment of inertia times the angular acceleration. Okay. We can do that. We're going to write down the total energy E as a function of phi. Do you guys want me to use the Lagrangian? I'm tempted to just use the Lagrangian for fun. And I'll do it later because we'll get to learn about the Lagrangian. Whatever, we have time. So the total energy is equal to 1/2 mv squared. But v in our case is the velocity along this line, right? So it's equal to the angular velocity times the length. Lagrangian, yeah. You guys want me to play with that? We can. I'll do that after doing this. All right. E equals to 1/2 m theta dot phi double dot squared L double dot squared plus mgl 1 minus cos phi. And we're gonna differentiate this guy with respect to time to get the equation of motion. And then that equation is the torque, yeah. Now we do know that this equation E is a constant because energy is conserved, which means that if we take the if we take the derivative with respect to time, it's going to be equal to 0. And it's also equal to the derivative of this whole thing with respect to time. So I take the derivative of this whole thing with respect to time. First of all, I'm gonna take the derivative of this term. It's gonna be equal to 1/2 ml squared theta dot it's gonna be 2 theta dot theta double dot. Because this is the only term that's dependent on time, so I moved everything to the left, and then took the time derivative of this one. Taking the derivative of this one gets 2 phi dot, and then by chain rule you also multiply by phi double dot. Over here as well is mgl. There's going to be negative mgl sine phi with phi dot, because 1 here, if I distribute this in, good sum for summation, by the way. Thank you so much. I spent like quite a long time on that one. Granted, my efficiency in terms of editing isn't very good, but thank you so much. I'm quite proud of it. We take the derivative of this one, and we take the derivative of this cosine. It's already negative, so it becomes positive again. And by the chain rule, you also multiply by phi dot. So now we have this whole equation of motion, which I can I just cancel out some of the terms? I absolutely can. But I'm not going to do that just yet. I'm going to format it in a way such that we get torque equals to I alpha. So I'm going to move this one over here, and then we're going to move, I'm going to keep this one here. I recommend flashback mod if you want to make more cinematic Minecraft content. Oh yeah, I've seen other streamers use that. I remember the flashback mod. I usually use the replay mod. Anyways, keep it up, man. Thank you so much. I'm gonna, yeah, I'm considering using the flashback mods because it's probably, I'm gonna compare them, I guess. I'm gonna be comparing them. Yeah, Minecraft mod. Yeah. MGL theta dot here are present in both terms, and the other side is 0. So I'm gonna divide this. I'm gonna move this guy to divide by 0. No, divide 0 with this guy, and then we're gonna, and so it's basically just canceling out the whole thing. So now we just have this one remaining, which means that ml squared theta double dot equals to negative mg l sine phi, which is equal to, give me a sec, which is equal to I alpha, and this one is torque, I alpha gamma, right? Because this is torque, because, you know, it's the cross product of the radial distance and the force acting on it. So this force is acting on it at this point, and the force is mg sine phi. So we we do the cross product, we get this, we get that this is a torque. So this confirms that it is a torque. For fun, I'm gonna use the Lagrangian as well. It doesn't look like that. I'm not used to drawing the curved L, like hold on. That look good? It doesn't look very good yet. Wait. I think that's like, yeah, I think that looks okay. The Lagrangian is typically written as T minus V. Or in this case U, because we're using U for potential energy here for this problem. So T is the potential energy. I don't know why it's called T. Funny Lagrange, yeah. So it's just the same thing. It's just m theta dot squared L squared minus mgl 1 minus cos phi. Okay, and now obviously it's just the same. We just plug this into the Euler-Lagrange equation. So first of all, I'm gonna write the derivative of L with respect to phi dot. It's gonna be equal to ml squared phi dot. Fun fact, this is the momentum. Well, the angular momentum. You see, if some people already know this, but when you take the derivative of the Lagrangian with respect to a coordinate, with respect to the velocity along that coordinate. So for example, this one is the velocity along the phi coordinate. What you're gonna get is you're gonna get the momentum along that coordinate. Along that coordinate. So if, for example, you use if you use x, it's gonna be the momentum in the x-axis. If you use y, it's gonna be momentum in the y-axis. So taking the derivative with respect to that coordinate dot, and you're gonna get the momentum along that coordinate. Next up, we take the time derivative of that term. And it's going to be equal to ml squared phi double dot. And this is just I alpha that we got earlier. Let's do the same thing for let's also take the derivative with respect to phi of L. What we get here is we're gonna get what? Hold on. You take the partial derivative, so this term becomes 0. This term minus mgl times 1 is going to be 0, plus cos phi is going to be 0. Plus cos phi is not going to be 0, it's going to be mgl sine phi. And because there's negative, they become positive. Then you take the derivative of cos phi, it becomes sine. It becomes negative sine. So we have that. And so we combine all of that. This is just the torque. And so we combine those terms together in the Euler-Lagrange equation. We get that I alpha minus torque equals 0. I alpha equals torque. Makes sense. So yeah, that's using the Lagrangian approach. Pretty much the same. For simpler problems, both are probably equally. Both approaches are probably like pretty much the same in terms of speed, but like for more difficult problems, like a double pendulum, Lagrangian is probably gonna prevail. So I have like over 10 messages on Discord for some reason. Give me a sec. Yo, apparently Dead by Daylight is releasing a killer Dead by Daylight is releasing a killer that's like based on a Thai mythology. Grimmy, hello, welcome to stream. Dang. Yeah, like that's pretty cool. So there's this in Thai mythology. It's actually Southeast Asian mythology. Like there's a lot of ghosts that have the same appearance. Basically, it's like typically it's the Discord phrase is spamming you again. There's like this like little woman with like intestines, with hearts, with like her innards flying around. Like apparently this is the killer that's gonna be added to Dead by Daylight, which is kind of cool. I think every Southeast Asian country has this ghost. I'm a big fan. Yep. I typically call that a windmill. A big fan. Get it? Okay. Question C. Assuming the angle phi remains small throughout the motion, solve for phi as a function of time, show that the motion is periodic with that period. Well, that's simple, because if phi is small, or phi is very small, we get sine phi is approximately equal to phi, which means that ml squared phi double dot is approximately equal to negative mgl sine phi. No, this is not approximately equal. It would be approximately equal to this, and then you cancel out the like terms first. Bloop, 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 bloop.ยังไม่ทำเลย Yeah, I have to do this real like ASAP because Silksong is coming out tomorrow. It's a very good game, so I'm gonna have to like start grinding my homework. as quickly as I can so that I would be able to do it. This differential equation is simple. Its solution is to diff equation is you probably already have heard of this before. It's simple. It's just A amplitude times the sine of square root of square root of G over L phi with some phase phi naught. This is the that's not E, that's supposed to be L. I just wrote it in a little curved way. Alright, so that's the solution to the differential equation. And so we can clearly see that omega equals to square root G over L. Period is equal to 2 pi over omega, because period is how long it takes to do one full revolution. Omega is the angular velocity, and one full revolution is 2 pi. So the period is going to be equal to 2 pi times the square root of L over G. And that is our answer, which lines up with the question. We did it, guys. We did it. Within 1 hour, we finished the classical mechanics homework. Clap, clap. All right. So we're not done yet. I have like a few more homework to do, namely the differential equation and advanced calculus homework. Which one should we do first, chat? Which one should we do first? Actually, which one? Clap, clap. Yay! Everyone's cheering for me. Yay! Which one did I put in the thumbnail first? Hold on. Did I put differential equation first or advanced calculus? I put advanced calculus first. Alright, then let's do it. I don't think I streamed this one, but I finished it before outside of stream because I didn't have the time to like actually stream it. I think I may have. I don't think I've done this one, so I'm gonna go ahead and do that. This section is probably gonna be a little more interactive now, because we're gonna be playing around with decimals as well. Differential, yeah. Differential? Wait. I put in advanced calculus first. Let's do advanced calculus. So, first of all, I'm gonna make like a bigger canvas. Probably gonna be like double the usual. What's 29 times 2 is 58. So it's gonna be 59.4. That's gonna be double the size of an A4 paper, i.e. that is the size of an A3 paper. And this is our first question for this differential equation, not differential equation, of this advanced calculus or Calc 3 homework. Sketch the level curves of f of x y equals to x cubed plus y plus 9y cubed. Well, this can, okay, the level curve for this guy is actually just an ellipse that is a little squished along the y-axis. This one's fairly simple. Nothing much about it. The reason for this is because this is, you can think of this as x squared plus 3y squared, which is a circle equation. This is a circle equation, and if it's constant, the level curve means that the function is constant. So if it's a constant, it means that it's going to be an ellipse. In this case, it's a circle. It's with the y-axis squished down 3 times by a factor of 3. So I'm going to show that on my decimals. Let me check my upper GX. Which one is it? Which page is it? It's this one. Why can't I find over gx? Not that window either. There it is, that window. There we go. It should be showing it. It should be showing it now. Okay, cool. So let's say f of x equals to x squared. No, x squared plus y squared. And then we set f of x, y equals to c. If I set c to be something, it's going to be equal. No, wait. C equals to f of x, y. Right? That did not work. Wait. Okay, there we go. I had to set it to absolute value. It doesn't really matter, but whatever. Because if I didn't do this, it's gonna interpret it as we define a function f that is gonna output c. That's what it understands. But if I set this, it means that you have to plot out the graph of f of x, whose absolute value is equal to c. So this is how we got this, and you can see that if I move this value c around, we get the level curve for this function. Obviously, our function isn't this; it's 9 times y. So the y here is squished by by a factor of 3. And obviously, if I move around the c around, it's going to look like that. And so that's the that's this graph. That's this question. So there's the level curve. The inner ring is going to be like some other. Hold on, my stream is delaying quite a bit. At least my phone is seeing a little bit of a stream delay. Can someone do a delay check for me? Actually, no, it's good. It's good. I think my phone just got disconnected for a second. I have my phone to like monitor my own stream. All right. So next question is sketch and shade the region where that function is continuous. Meow. And how long does that take to spawn? Okay, not too long. I think that's okay. Good enough. Sketch and shade the regions where this function is continuous. How does this function look? It doesn't really matter. What we care is if it's where it is continuous. Well, we immediately know that when we have a fraction of something, right? The thing that's probably going to make it not continuous is the one down here, because once it's 0, that point is undefined. So here we can see that we can immediately realize that that's when the function is going to be not continuous. Discontinuity is going to be at x squared plus y squared minus 9 equals 0, which means that as x squared plus y squared equals 9 is the discontinuous point. In fact, it is undefined. What am I typing? Not what am I writing? Discontinuous point. And this is just the equation that we just plotted. This is just a circle equation, which means that the function is going to be split into 2 zones. I'm using the circle tool for this. Hold on. The function is going to split into 2 zones. The function is going to be split into 2 zones. The inner zone is continuous, the outer zone is continuous, but it's not going to be continuous in between. And so I'm going to like color it or something, because it told us to shade the region. So inside here, the inside of the ring is not continuous, and the outside of the ring, the inside of the ring is continuous, the outside it's also going to be continuous. But in the middle, like at the dashed line, it isn't. Gonna make that coloring part like a little less, there we go, more transparent. And that's our answer. Simple enough. And that's our answer. You know what, because I already had Desmos open, in fact I'm gonna use Desmos 3D. Use Desmos 3D, and because I'm also curious as to what how the function looks like in 3D. So it's x minus y, right? X minus y over x squared plus y squared minus 9. And this is, hey, welcome, review, welcome back to the stream. I'm doing a marathon stream, Funny Graph website with 3D, yep. I'm doing a marathon stream because Silksong is coming out. I need to get my homework done so I can play video games at 100% efficiency. And this is how the function looks. The function, you can see that on the inside the function is completely continuous. On the outside the function is also completely continuous. But like at the circle, scary looking graph, it is. I don't know why it's ripped like that. Like it's probably some Desmos bug, but it does look scary. So like the x silksong tomorrow, yeah, x squared plus y squared equals to 9. There, in this region, this is the region at which the function is not continuous. Do I have Desmodder on in this profile? I don't think I do. Oh, okay, damn it. Because like Desmodder is like a very cool Desmod mod. Man, it's legit speedrunning homework before Silksong. Yeah, come on, I need to play Silksong at full efficiency. Yeah, okay, so that's that. So that's this question. Moving on to the next question. It's just, at least we can say that we got Silksong before GTA 6. Yeah. GTA 6 is coming out next year, right? Okay, paste, there we go. I pasted it on the wrong layer. Okay, consider this function, find fx, fy, fxy, fyx. You know. Okay, so what this means is just, first one here means find the partial derivative of f with respect to x, where x equals 0, y equals 0. So let's just do that. We take the partial derivative. We take a partial derivative, and we get 1 plus y squared e to the xy squared. 0, 0. And we set x to 0, y to 0. We're gonna get what? We're gonna get 1 plus y set to 0, so that term just becomes 0. So that becomes 1. Question A is 1. That's simple. Okay, advanced calculus isn't that difficult for these for the few homework. Last time the homework before the advanced calculus homework before this was much more difficult. Okay, fy derivative of f with respect to y at point P 0, 1. So we just do that. We treat you know how to take you guys know how to take partial derivatives, right? You just take the derivative, just setting the other variables as constants. So taking the derivative of f with respect to y here, just treat that x here as constant. So that's going to be e to the power of xy squared, and then multiply that by the derivative of the inside. The derivative of the inside is going to be equal to 2xy, I think. Yeah, and then setting at points 1 and 0 and 1 means we set x to be equal to 0, which means it's going to be equal to 0. Should I listen to this while doing homework? Yes, you should. It's gonna make you have slightly more IQ to do homework. Trust me. I also need views. Derivative, but only partially. That is not untrue. So here we are taking the fxy and fyx. Spoiler alert, it's gonna be equal, but I just heard something explode. I don't know what it was, but we take partial derivative. For your information, taking partial derivatives is commutative. That means no, not is it commutative? Is the word correct? Like you can change the orders. I don't think the word commutative is the exact word. Like it doesn't depend on the order. So in this case, the derivative of f of x, it should be equal to. Yeah, in the end, it should be equal to each other. So I'm gonna do this first, which we have already taken the derivative of, which is going to be 1 plus y squared e to the x y squared. In this case, it's going to be equal to, oh boy, this is going to be a bit of a pain. It's going to be y squared. In other words, is commutative. Okay, so I think I used the right word then. This is going to be a bit of a pain because now I have to take the derivative of two terms. As per the product rule, that's not x, that's supposed to be y. Yeah, e to the xy squared. E to the xy squared, yeah, we already have that. This one becomes 2y e to the xy squared. This one becomes y squared times this times 2xy times e to the xy squared. Because this derivative here we calculated this prior, so it's going to be equal to that. And now we just how much space do I have left? Okay, quite a bit. So now we have 2y e to the xy squared plus 2xy cubed e to the xy squared. And that's that. Now let's take the derivative with respect to y first and then with respect to x. That is, we grab this and then we take the derivative with respect to x. F by dx. And what we get here is going to be equal to, we take the derivative with respect to x of 2xy e to the xy squared, which we can split into, as per the product rule, we can split this into 2xy and multiply by the normal e to the xy squared, and then add the normal to xy, and then the derivative of exy squared. And this term is going to become 2y e to the xy squared. And this term is going to become 2xy times y squared times e to the xy squared. And then this is going to be equal to 2y e to the xy squared plus 2xy cubed e to the xy squared, which is equal to what we had earlier. And that confirms it. Alright, we're speeding through this homework. I think we're speeding through this homework, kinda. Find a local linear approximation for, oh, I haven't screenshotted the question. Wait, hold on. Give me a sec. Find the local linear approximation for this guy at point 1, 1 of camera homework. Okay, so local linear approximation, what does this mean? It means that basically if you have some function, right? we have some function, you know, let's say this is a 2D function we have, and then we move linear approximation. If we move along the x-axis, hold on. If we move along the x-axis, let me just zoom in. This dx, we move along dx. How deep will f be? This ratio, okay, moving along just dx, just x. This ratio is the partial derivative of x. On the other hand, if we have this function, but then we move along dy instead, give me a second, I have to erase this. Okay. On the other hand, if we have the dy or something like that, if we move along the y-axis, how high does the fx go up? There's the df, there's a lot moving along dy, and that the ratio between this is equal to df by dy. The local linear approximation here is equal to the total change. If you move along x a little bit and you move along y a little bit, then you add them up. That is, let me write that. Boop. This is how much that the height changes as you move along x. This is how much the height changes as you move along y. Now, obviously, this value will change if you move along x first. If you move along y, this value is going to change. But we're using linear approximation here, which means that we move very small enough to the point that we are assuming that the function doesn't change that much. So the overall change in the function can be approximated with linear order, in linear order terms. Which means now we're going to have to find df by dx, df by dy. And we can't do that. We can just use... You know how to differentiate that, don't you? It's just 2x dx plus 2y dy. And in the end, we're going to set p equals to 1, 1. But right now, we just have this. And this is what we have. Now df here is just the function of the point of interest, right? Minus the point where we started off. The point where we started off being this point. And this dx again is the change, is how much we move along the x-axis. So the x value, so dx here is how much we change along the x-axis, which is equal to the current x we are and subtracted by the original x we were at. And the same goes for this one. And now we just plug in the numbers. We want it at point p11, which means we just plug in x1 equals x naught equals to 1, y naught equals to 1. F0 here is equal to 1 squared plus 1 squared equals to 2. So now we have f minus 2 equals to 2x times x minus 1 plus 2y times y minus 1. And this is our approximation. Let me just move that real quick. Let me just move the 2 over there. So this becomes f of xy is going to be approximately equal to 2x times x minus 1 plus 2y times y minus 1 plus 2. This is our answer. This is our linear approximation of this function. And I'm going to show that x squared plus y squared is going to look like that. And our linear approximation is what? Okay. And our linear approximation, my phone is very much off. Okay, hold on. My phone is not connected to the best Wi-Fi right now. Hold hold on, let me connect my phone to a new Wi-Fi so I can so my like stream on my phone can be up to date. So the function here is going to be equal to f of xy must be equal, one sec, f of xy must be equal to 2x times x minus 1 plus 2y times y minus 1 plus plus 2. I think something's not right. It's not right because I completely forgot about the fact that this is not it yet. We also have to plug in 2x there. We also have to identify that this is y. Why not? We also have to identify that those are those. So this becomes 2 times 1. This becomes 2 times 1. So the actual, hold on, I forgot to. Okay. So the actual number actually should be, so now we just change that to this function. And here, as you can see, that at point p at 1 1 f 1 1, the point over here can be approximated by this plane. You can see that this is basically the tangent plane to the function, and that is how you can approximate a function linearly for multiple input, for functions of multiple variables. So that's that. Next question is the total differential. Yep, it is cool. So, you know, this is, one sec. So what this thing is, this term that I have right here, is known as the total differential, which we'll be doing over here as again. And for your information, the concept of total differential is so important in physics. That's like, you use it in pretty much everything. Not just physics, engineering as well. Yesterday, I explained to my brother how inverse kinematics, you have to use this concept of total differential to do inverse kinematics. This is how robots literally just walk and shit. Robots don't shit yet, but like walk and do stuff. Yeah. The total differential is equal to the derivative of f with respect to x dx plus derivative of f with respect to x with respect to y dy plus df with respect to c. And that is what the total differential is. This will you can, like, this one has so much potential because you can use it in terms of inverse kinematics as well. For example, like the position vector is going to be the position vector with respect to like the angle of a joint or something. Like for example, if we have a robot joint, right, and we have at the end effector right here, and this vector is going to be r. If we know that if the object moves over here, if the end effector moves over here, we can use this to find the angle of the joints that we need to change. Like with this, we can find the angle that we need to change. So this concept is a very important concept. This is also used a lot in general relativity, of course, which I've been studying recently. And I actually want to show off you guys what I did with what I learned from general relativity. But for now, let's just solve this equation, not solve this problem, which is just going to be the derivative of f with respect to x here. Keep these guys as constant. This guy's the only one being taken the derivative of. So it just becomes that. This one, the same applies. Relativity, well, yeah. it's pretty fucking cool. What I did, I think, in my opinion. I'm also making it into a full-blown video as well. So stay tuned for that. Yeah. Take the derivative there, so it becomes e squared y squared cos c dc, and this is gonna be d of f, and this is our answer. That's it. It's that simple, chat. This has been pretty easy so far because, well, there's the homework for this curriculum. Yeah, curriculum. I think it's pronounced like that, right? It would be stupid if it's pronounced otherwise. Right. So this is homework set 2. Homework set 1 I did this earlier, like a few weeks ago, when I genuinely like fell asleep on stream. Curriculum, yeah. But this one is the second, and it's much easier because now we're in the actual content now. That one, he was just testing the waters. Okay. I honestly don't know how to do a few of these. Well, you know what? First time for everything. I haven't done these before, so let's just do that right now. Prove the following identities. So A, we have that, and B, we have that. We have to prove that this following identity is true. So for general, so for A, remember the cross vector? I did this like a few pages ago. Yeah, remember the cross product here. This here might not be just the novel operator. If it's cross product, it's just the first vector times, like, if this becomes A, this won't be a derivative with respect to Y. It would be the Y component of A. This would be the C component of A. There would be C component, X component, Y component, instead of the partial derivative. So in this case, we're going to have A dot product with the following. We are going to have B y c z subtracted by b c c y, and then we have b. Hold on, let me think. B c c x subtracted by b x c c, and then this is going to be b x c y subtracted by by cx, and this is equal to ax by cz minus ax b c cy plus ay b c cx minus ay bx cc plus b ac. This is a little tedious, but I can make this better. I can make this look better by using tensors. But I'm not sure if you guys will get it or not, and I don't know. But I feel like if I explain it, it would take forever. So I'm not gonna do that just yet. Why is that? That's not C. That's supposed to be Y. Okay, is that everything? That's a Y. Why is that C? That's C. That's supposed to be CX. Yeah, that's everything. You can prove this yourself that the rest is going to be true. I think Professor forgot to put that there. You can just regroup it. If you can group it in this way. If we group it with respect to B, right? If we group BX, what we're gonna get is we're gonna get ACCY minus AYCC. If we group it with respect to X, and then next is gonna be BY, and this is gonna be AX CZ minus A C CX. As you can see, I keep jumping between the two pronunciations of the letter Z or C or Z. Keep jumping between the British and the American version. And if we group out the BC, we're gonna get AY CX, and then subtracted by AX CY. In this case, it's gonna be equal. It's gonna be equal to B cross C cross A. That's not cross. I said it wrong. It's supposed to be dot. On the other hand, if we group it by C, it's gonna be equal to C. What is it? If it's CX, it's gonna be minus BYAC. That means it's gonna be A cross B. Right? It is A cross B. Yeah. I knew that immediately because there is the CX term has negative ACBY. Its negative ACBY means that if the Y comes first, if it's in reverse order, so like if the C is in there, okay, it's gonna be negative if the in front thing is behind that thing, if that makes sense at all. Like if it's like if A is in front, then it's gonna be negative ACBY. If B is the one in front, it's gonna be negative BCAY. So I immediately knew that this is gonna be the case where A is in front. So that's the first identity. The second identity is quite a little bit. I'm gonna actually prove this identity in a different approach again, in another approach. So give me a second while I think, because I kind of forgot. Okay, yeah, I remember now. So basically, in tensor notation, which I learned from general relativity, A dot BC, B cross C here is going to be equal to A times the A dot the vector, and that vector can be written in terms of tensors. The cross product is going to be Levi-Civita symbol. And then there's going to be there's just a little bit of a fun little fact. Just don't take this one seriously. Like it is true, but like don't take it too seriously. And it's gonna this is Levi-Civita, so this is gonna become dotting. It becomes joining the becomes adding up the indices. So this becomes AKBICJ, which is equal to if I permute the indices. If I permute the indices, this becomes AJ BK CI, which in this case is going to be B dot the cross product between C and A, which has been proven. And we can also permute it again to get AI BJ CK, which means it's going to be equivalent to C dotting A cross B. Alright. And that's that. Someone pinged me on Discord. Oh dear God. Okay. So that's the proof for the first identity. Next up, we're going to prove the next identity. I feel like I'm going to finish this one and then I'm going to do the I'm going to finish this one and then finish this first question, and I'm gonna discard the rest because I'm starving. I'm actually starving. So I'm gonna finish this one and then go and then do the differential equation, and then do the differential equation homework, and then I'm gonna go. So I'm gonna finish the advanced calculus here, because technically this advanced calculus homework problem set is actually like 1 week, no, 2 weeks in advance for deadline. So we're gonna prove the next identity. A cross B cross C equals to B A dot C. Let's just prove that, I guess. Okay. A cross B cross C is equal to A cross copy and paste. Okay. Yeah, my homework for this subject is technically 1 week in advance already, so I can just chill out with this one. Yeah, because this I think it's because this homework that I did earlier. Yeah, this homework, these five problems it's actually due next week, so I'm like 1 week in advance. So this is this question I'm doing is actually due in 2 weeks, almost 2 weeks. If I do that, it's gonna become the cross product is gonna be AY times that thing. No, times that thing. So it's gonna be AY BX CY subtracted by AY BY CX. All of that subtracted by AC times AC BC CX subtracted by AC BX CC. Interesting. Alright, and this is the first component. And the next one, this is going to be this is going to be one hell of a thing. There's going to be one hell of a whatever. It's going to be AC. This must be, okay, so it's AC. So this is going to be the x component of the second vector, which is going to be BY CC subtracted by AC BC CY. Of that subtracted by this is the x component, so it's going to be AX and then it's going to be BX CY subtracted by AX BY CX. And then the next term is going to be this one, so it's going to be AX times this one, so it's going to be AX times BCY. Is that oh yeah, okay, that's correct. Okay, BCCX subtracted by AX BX CC subtracted all of that subtracted by AY BY CC. No, CC. Subtracted by AY BCCY. Boop, and that is our product. So that's the final vector. And we have to prove that it's equal to this one, which shouldn't be a problem, I think. I don't think it'd be a problem. Yeah, okay. So here's what I'm gonna do. I'm gonna pull out the like terms. So for example, no, like okay. So what? This is gonna be. Hold on. Hello, test. Okay. This is equal to This one we have AY and CY. We have just one BX. And we are in the slot for the X axis, for the X component. So this one becomes AY, CY, and we have another BX over here. So this becomes AY, CY minus AC, CZ. It's actually plus because this is minus. This is minus. Because this is minus, it becomes plus. And that becomes, it becomes that times BX. And then the next term we have CX. We have the same thing for CX. So we have AY, BY. This is actually negative. Yeah, there's negative. This is also negative, so this becomes positive. And so the negative over here will distribute in. And so that's going to be AC, BC, and this is going to be CX. And the same applies for the other axis. And this, so this one becomes A dot C yeah, A dot C B subtracted by A dot B C. And that's our answer. Okay. Here you can see that there is no AX, there's no AX CX term, but that's because if there's going to be AX CX term here, but it's going to cancel out with AX BX CX term over here. So this will end up being equal. And that's our answer to question 1 of the next week's homework. All right. Well, that was quite a bit tedious, but it could be made more easily. It could be made simpler, right? I think it can. Hold on, give me a sec. If I use the Levi-Civita symbol, IJK, right? This is gonna be the let me test something out real quick. Cross product. I'm gonna say that D equals to B cross C, which means that the K component of D is equal to the Levi-Civita symbol of I, J, K. Wait, so the tensor index, the index should be up here. Okay, sorry. So this becomes that. It becomes BI and B and CJ. And then A cross D is going to be equal to the Levi-Civita symbol. I'm going to use alpha this time. Alpha, beta, gamma. Even though we're not considering 4D space right now, but like it'll probably work. Like it doesn't really matter. We just consider that this goes from 1 to 3. Boop, boop, boop. And that's going to be equal to Levi-Civita symbol alpha beta A alpha times epsilon beta ij bi cj. And now I have to find a way to prove that this will be equal. Funny symbols, yeah. Welcome to tensors and shit. And I will have to find a way to prove that this is going to be equal to you'll find a way to prove that this is equal to AI B. I'm too lazy to do this shit. You know what? I'll just call that a day. This is enough for me. So that's this subject homework done in advance. So now on to the last question, which is, oh shit, differential equations. On to the last subject. Solve the following ordinary differential equations. Again, I'm going to make a new page. There's going to be differential equation. It's not hard. The problem is the fact that it's tedious. As you can see, this is a very fun looking differential equations. So right now I'm considering how are we going to solve this, because it sounds like a pain. Well, it is, because there's I could use Laplace transform. Fun, yeah, fun, totally. Fun a triple prime. Yeah, there's a fucking third derivative, which is not something you commonly see, but I guess that happens. How do we do this? I feel like there are actually like several ways to solve this. Oh, right. I'm gonna use the method of annihilators. Wait, would that work though? Wait, hold on, give me a second. Or should I use a different? You know what? I'm gonna use the method of annihilator for this one. Sounds like a cool name, but it's tedious as fuck. Let me explain. What we do is we're gonna write this down. We're gonna say that dy equals to d by dt of y. So that means this operator here, d triple prime, okay, y triple prime, y double prime, y prime here is equal to d cubed minus 2d squared plus d operated on y. Oh boy. And it's going to be equal to t cubed plus 2e to the t. So that's fun. What the strategy here is, we're going to use this thing to find a way. We'll find a way, just eventually. Just give me a moment. We might be here for quite a bit, quite some time. Okay. Let's see, how can we do this? So the method of annihilator is to annihilate the right hand side by operating on it. For example, t cubed here, if you operate on t cubed like 3 times, what happens? If you operate on t cubed 3 times, the result is gonna be the first derivative you're gonna get 3t cubed. The second time you take the derivative, it's going to be 6t. And the third time you take the derivative, it's going to be just 6. So, I forgot, I'm supposed to use to the power 4 here. So we operate on it 4 times. This becomes 3 instead. This becomes 2. This becomes 1. And this becomes 0. So we do know that if we operate on this guy on this right hand side 4 more times with the differential operator d4, then the right hand side, the t cubed prime, will disappear. In the same sense, if we have d minus 1 operated on e to the t, what happens then? What happens is we're going to have the derivative of e to the t minus just e to the t. The left hand side becomes e to the t because the derivative of e to the power t becomes 0. Becomes e to the t. And then you subtract it by e to the t becomes 0. That means if we use d minus 1 here, operate on both sides of the equation, e to the power t here disappears. So if we do d to the power 4 here, operated on both sides of the equation, it will get rid of the t cubed term. And after that, you operate this thing on both sides of the equation, it's going to eliminate this term. So the right hand side will become 0. So let's proceed to do that. Let me turn this into d to the power 4. And then I use d minus 1. And then this left-hand side is operating the d operator on the y. It's going to be equal to d4 d minus 1 times t cubed plus 2e to the t. And it should be equal to, the right-hand side should be equal to 0. It should be. Yeah, it would be. Because you take this derivative, this one becomes 0. This will become some random polynomial, but that random polynomial is going to have a degree of 3. Which means you take the derivative 4 times, it's going to disappear. On the left-hand side here, we write that as y. And we have d to the 4, we have d minus 1. This thing, you can factor it out, it becomes d. And this one becomes d squared minus 2d plus 1. Oh boy. And this one will become d to the power 5 because operating... Wait. Does it commute? Oh my god, I hope it does. Okay, wait, hold on. I need to prove that the differential operators commute. Wait. If we have some operator O here, O1, O2, acting on y, it's going to be equal to O2, O1 acting on y. I have to prove that this is commutative. This one will become no, this one becomes O1. Why did I write Q there? O1, and this is going to be some derivative of y. So it's going to be d to the power of n. No, constant. I'm going to cn d to the power of n y plus, and no, I can write this as a sum of n with cn d to the power of n operated on y. Yeah. These two becomes this. This one will become O1, so this will become a sum of m dm y. I have to prove that they will be equal. So now I have to prove that this becomes hello, paint.net, please. Hello. I think my mouse suddenly stopped moving. This is, I'm gonna use another constant. I'm gonna use k. We have to prove that km here, d to the m, n, cn d to the n, y is equal to m km d to the m sigma n cn d to the n y. No. Yeah, you can pull out the summation sign and it becomes equal. Alright, cool. Okay, yeah, we the linear differential operators are commutative. Perfect. That's great to know. This one also becomes d minus 1 to the power of 3. Because this one can be factored out as d minus 1. Y equals to 0. The strategy, the next thing we have to do here is we have to assume y equals r. We assume y equals to e to the power of rt. If we do that, what happens? to this equation. What's going to happen to this equation is that d to the power 5 d minus 1 cubed on y equals 0. This left hand side here is going to be equal to r to the power 5 times r minus 1 to the power 3 equals to times y equals 0. You can test this out yourself. I'm pretty sure that is true. Yes, it is true. Okay, it is true. So this, it will become this. Yeah, it is true. It will become this, which means that therefore there are multiple y's. There are multiple r's possible. The first r is equal to there are 5 r's that are 0, and there are 3 r's that are 1. All right. What you do here is you're going to end up with 8 y variables. Y here is going to be equal to e to the power of 0t plus, and then the next term you would have to multiply by x, because to make sure that the value doesn't get duplicated. And this term as well, this becomes 0, so this the value, if I multiply by x, it becomes e to the power of 0t, but here x e to 0t is already applied. No, why? No, not x. What am I saying? It's not x, it's t. This is t. This is going to become t squared, because otherwise the t, if this was just 1t, it will be duplicated. It would be duplicate of this answer, of this term. Because if we have 3t to the power t squared here, okay, hold on. Let me, I'm going to be back to explain that. Give me a sec. This is going to be t cubed, this is going to be t to the 4 e to 0t. And of course there's going to be constants here. Constant 1, C2, C3, no, C2, C3, C4, C5. If we only had this, if we only had one, if we didn't have all these terms, then we wouldn't have needed d to the power 5. Differential equations, yes, this is a differential equation. We're using the method of annihilators, which sounds really cool, but it's really fucking tedious to do. Okay, d to the power 5 here. If we had just this term, if we had just 2 of these terms, we wouldn't have needed to use the differential operator 5 times. Yg plus ye. Yes, that is actually no. That's not the. Well, in a way, yes. So like when you have differential equations, the general form plus something, yeah, plus the particular solution. So in our case, we do have the we can find the general form and particular solution. I took this course last semester. Nice. Yes, that is how. How do I crash course? I don't really know. I think there's a few good books out there that you can, like, if you have taken it before, you can just go right read through it. You can just probably like read through it and be reminded of some of the concepts. Next term, of course, becomes e to the power of 1t. The next term becomes e to the power 1t as well. But because these 2 terms will be duplicate, we would have to multiply by t in front here. Again, if we didn't multiply by, if we only settle with this guy, we would only need one. Which year is this? This is second year. Yeah, this is second year of university. If we didn't have t over here, if we only have this one, we wouldn't need to operate on it 3 times to get rid of it. Operating on it once would have gotten rid of this one. So if we operate on this one twice, it will also get rid of this term. Electrical engineering, no, just straight up physics. I'm a physics major. This becomes so this becomes t squared e to the power of t. So if you operate on this with this thing 3 times, it will disappear. This term disappears. So now we have what? Fucking no. We have 8 fucking constants to deal with. That's pretty neat. Yeah, it is really neat. Physics is fun, and then you sometimes have to deal with this, where you have to solve for 8 fucking Jesus Christ. You have to solve for 8. Oh my god. Am I allowed not to? We only have written homework, Lamau. This actually, I could do this. Actually, I could type this out in LaTeX. No initial conditions. Yeah, the question didn't give us initial conditions for us, but it doesn't. But the particular solution will have. It's pretty much complete. No, not yet. The particular solutions will have. Will have set constants. So these constants aren't done. We're not done with these constants. The first few terms, yes, but the particular solutions we still have to solve. So let's see what we gotta do. There's the right hand side. Yeah. All right. So let's have fun. I guess I'm gonna rewrite the equation to make it look prettier. What we have is gonna be t to the power 4, because this one is just a all of these, this is just a polynomial, right? So this becomes I'm gonna call it a instead. No, just call it, I'm gonna call it c. C1. All right, good luck, man. I have no memory. Good and gone. All right, see ya. C2 and then multiply by t. C3 multiplied by t squared plus C4 multiplied by t cubed plus C5 multiplied by t to the 4, because e to the power 0 t is just 1. This term becomes 1, so all of this becomes a polynomial. And then we also have, this one is a bit of a pain, but it should be fairly simple if I could exploit the fact that this is a polynomial. This one becomes t squared, and then all of that multiplied by e to the power of t. All right, and that's y. And now we find each of these by by equating the coefficients. So what we do is we operate this thing on this whole. We do this operator on y, and then we get this, and then we compare them to this one. So before we do that, this term looks like it's going to be a pain in the ass. So because this term is going to be a pain in the ass, let me prove something real quick. If I take the derivative of some polynomial function x times e to the power of t, this polynomial function is of t, sorry. Question is, what are we going to get? What we're going to get is we're going to get p prime e plus p e, because there's that, so it's going to be equal to p primed plus p multiplied by e to the power of t. All right, that's cool. That's a good thing to keep in mind. And now we have fun. So what we have to do is we have to take the derivative of y 3 times, and then subtract it by the derivative of y 2 times, and then add it by the derivative of y once, and we have to equate it to this. Oh boy. So first derivative of y is going to be equal to c2 plus c3, no, plus 2c3 plus 3c4 t squared plus 4c5 t cubed, and then plus this term. I have to take the derivative of this term, which is actually something we proved earlier. It's going to be equal to the original polynomial, c6 plus c7t plus c8t squared plus the derivative of this, the first derivative of this polynomial, which is equal to c7 plus 2c8 t, and that becomes e to t. And this is the reason I made the paper a little bigger this time. So this becomes, I'm gonna move the whole, copy that, and then I'm gonna group up the polynomials. This becomes c6 plus, this becomes c6 plus c7 plus c7 plus 2c8 times t plus c8 t squared. Okay. Next up, the second derivative of y is going to be equal to 2c3 plus 6c4t. Are you guys having fun? I'm having a lot of fun. Totally. And there's going to be, again, that's the same thing. Just the same polynomial, but actually, wait. The same polynomial. So it's going to be c6 plus c7 totally. Yep, that is fun. Slash s. c7 plus 2c8 t plus c8 t squared, and then plus the derivative of this guy, so it's going to be plus c7 plus 2c8 plus 2c8 t, and then this e to the power t. And I'm gonna shrink that down a little bit. Actually, I'm gonna move this over here first. And so I could write this out. Which is it's going to be equal to 2c3 plus 6c4 plus 12c5. This t squared plus c6 plus 2c7 plus 2c8 plus c7 plus 2c8 no, plus 4c8 multiplied by t, and then plus c8t squared, and then e to t. Okay. Okay. And d cubed y is equal to 6c4 plus 24c5 t plus, oh god, when will this end? Why am I here? Okay. Plus, and this is gonna be quite big. Actually, no, fuck it. I'm gonna just take the derivative in my head. So this is gonna be c6 plus 2c7 plus 2c8, and then if you take and then you add, and later on you have to take the derivative of this guy and add it. So the derivative of this guy is gonna be that. So we're gonna end up with c6 plus 3c7 plus 6c8. I think I'm starting to see a pattern. But yeah. And then this term is going to be added with 2c8. So it's going to be c7 plus 2c8. No, plus 6c8. And you multiply that by t to the power of 1. And then you still have c8 as t to the power 2. Okay, I think that's right, according to our formula that we just got earlier. This is e to the power t. And we're not done here because we have to also set up the equation now. This is just the d to the n, d to something. We haven't finished it entirely yet. So, d cubed minus 2d squared plus d. So, 6c to the power 4 plus 24c5t plus e to the power of t times something. So that something is going to be c8t squared plus c7 plus 6c8 t plus c6 plus 3c7 plus 6c8. My hands are a little tired. Okay, and then subtract that by d squared y, which is subtract that by 2d squared y. So that's going to be subtracted by 6c3. No, this subtracted by 4c3. 4c3 minus 12c4t minus 24c5t squared. Yeah. And then subtracted by e to the power t, and then on the inside it's going to be 2c8t squared plus 2c7 plus 8c8 times t plus 2c6 plus 4c7 plus 2c8 plus 4c8 because it's multiplied by 2. And then you plus 1, you plus d, which is going to be plus c squared, plus c2 plus 2c3t plus 3c4t squared plus 4c5t cubed plus c8t squared plus c7 plus 2c8 t plus c6 plus c7 times e to the power of t, and it must be equal to t cubed plus 2e2t. T cubed all of that for this little guy. Oh, okay. And this is just question 1. We still have another question to do. Granted, that other question is probably I do have a strategy for that one. And it should be a little easier, I hope. Yeah. Let's see. So I'm gonna combine everything, every term together now. And we're gonna learn that วิชาอะไรอะ a differential equation. This is DE, yes. This is DE. So now we immediately know that CE is arbitrary. C8 is arbitrary because actually no, C8 is not arbitrary. We know here that this term C7 plus C6, C7, okay, hold on, plus C8, plus 6C8, C7 plus 6C8 subtracted by 2C7 subtracted by 8C8 and then added by C7 and then 2C8. There's going to be the t term. That's going to be multiplied by e to the power of t. First of all, it's going to be 0t squared plus that. And then the one in a polynomial is going to be c6 negative 2c6 plus c6. So the c6's cancel out. Next up we have 3c7 minus 8c7. So 3c7. 3 minus 8 is equal to minus 5. And then plus c7. So it's going to be minus 4c7. I think that's right. And then 6c8 here is going to be, this is a 6c8, which is going to match up with 4c8 over here. That's 4, right? That is 4, yeah. 6c8 is going to be cancelled out by negative 4c8, so it's going to be 2c8. So it's just going to be that. Wait, no, I'm stupid. Hold on, I'm sorry. Wait. Give me a sec. Let me do that again because I already distributed the 2 in. I didn't do that for C2. Okay. C6 plus C6 minus 1 C6 plus that will be 0 C6. 3 C7 minus 1 C7 plus C7 0. Okay. 6 C8 minus 4. So that would be 2 C8. So 6 minus 4 equals to 2c8. So that's plus 2c8. And you multiply that by e to the power of t. So 0t squared plus all of that thing combined times t and then plus 2c8. And then the next thing is the polynomial terms. Let's see what we got for the t cubed is going to be 4c5t cubed. So we immediately know that that's the only t cubed term. Next up is t squared terms. Let's see what do we have for the t squared terms. For t squared terms, there's none here. There's only there's negative 24c5, and there's 3c4 minus 24c5, and that's the t squared term. And then the t to the power 1 term is going to be 24c5 minus 12c4 plus 3. C4 of that, and you multiply by t. Wait. No, that's plus 2 C3, sorry. Should have been plus 2 C3. I looked at the wrong term, sorry. Alright. Plus 2 C3. And lastly, the constant terms, we have 6C4 minus 4C3. So 6C4 minus 4C3. And then plus C2 equals to t cubed plus 2e to the t. There we go. Alright. And now we can solve it, because we do know that this whole thing, give me a sec, this negative 8, this is all 0, so this becomes C8 is going to be equal to 1. Why? Because C8 here multiplied by 2, and then you multiply by e to the power of t is equal to 2e to the power of t at all points. Therefore, C8 is equal to 1. Now we have that answer. Next up, C5 is equal to 1 over 4. Because, again, we use the same argument that the coefficient in front must match. Has someone messaged me on Discord? I saw some. Okay. And then the rest is just solving the equation. So I'm going to go ahead and do that. 3C4 minus 24C5 equals to 0. Right? Yeah. So that means 3C4 is minus 6 is equal to 0, therefore C4 equals to 2. Okay. I'm gonna start circling the, hold on. I'm gonna circle all the final coefficients so I don't get confused later on. And then the next term we have 24C5 minus 12C4 plus 2C3 is equal to 0 because there's no t to the power of 1 term on the right. Now we already know that C5, that's going to be 6. We already know that C4, that's going to be negative 24. But we don't know what 2C3 is. So that means C3 is going to be equal to 18. Because that becomes negative 8. No. 2C3 becomes 18. That means C3 is going to be 9. And then I'm getting a little suspicious because we are having a few too many terms. We shouldn't really. Oh, never mind. Yeah, we got this. Okay, nothing. I'm just tripping. We also know that 6C4 minus 4C3 plus C2 equals 0. Because this constant term, there's no constant term on the right. C4 is that one, so it's going to be 12 minus 4, that's going to be 36. Plus C2 equals 0. Therefore, C2 is going to be equal to 24. And so we have the unknown variables, that is going to be C7. The unknown variables is going to be C7. There's going to be C6. And there's going to be C1. Yeah, and C1 doesn't appear in the equations at all. So therefore, we're going to have 3 unknown variables, which corresponds to the three derivative orders, which we expected. Alright, so now it's time to write out the final equation. This is going to be t squared. This is C8. 1 times t squared. Plus some constant terms. I'm going to call it C7t plus C6. And that's not all, actually. Is it? No, okay, that's all. Okay. So this is our answer for y. Y equals this. And then e to the power of t. And then we have plus 1/4 t cubed plus 2t squared. Not 1/4 t cubed, actually, it's 1/4 t to the power of 4 plus 2 t cubed plus 9 t squared plus 24 t plus some arbitrary constant c. And this is the answer to our differential equation. Yay! Fucking finally. God, I don't want to do this in the exam at all, man. What the fuck? Alright, whatever. Time for the last question for today's stream. Guys, clap for me. Cheer. Finally, bro. We're not even done. We have one more question left. Oh, God. We have one more question. It's this. You love this, right? Yes, I'm having a lot of fun. I'm having lots of fun here. Oh. Okay. Chat, here's what I'm gonna do. I'm too lazy to do all that shit over again. So what I'm gonna do is I'm gonna... Wait, do I need to do that? Hold on, I might not need to. Oh, that's still gonna be a pain though. Okay, you know what? Here's what I'm gonna do. I'm gonna use Laplace transform on this. So first of all, Laplace transform on t is gonna be equal to 1 over t. If I remember it correctly. Wait, hold on. The definition of Laplace transform is integrating over from infinity to infinity minus s and then fx. If I remember correctly. Minus st fx d. No, not f of x. It's gonna be ft. Minus s. There's gonna be dt. Right? Right? I'm quite sure it is. And so this one on this side will become. So in the case for f equals to t, what we're going to have is we're going to have the integral of e to the negative st times t dt, which you can turn it into, sorry, this wasn't supposed to be 1 over t, this was supposed to be 1 over s. Right? Because this just becomes negative 1 over s times the integral of t e to the negative st. No, wait, no, fuck, sorry. T e to the negative st. Is that right? That's 0 to infinity, right? And yeah, I think that's right. If I distribute s if I put s in there, it's gonna become. To make sure, hold on, I'm just gonna straight up Google here. Laplace transform table. Why did I type that? Laplace transform table, I'm pretty sure it's 1 over s. I'm just checking to make sure that it is indeed 1 over s. That's not right. Hold on. Table of Laplace transforms. Yes, very readable. Thank you. Yeah, it is. Is it? No, it's if ut. TUT was what? Oh no, if it's t, then it becomes 1 over s squared. If it's just 1, it would be. If it's a constant, sup gang, bye. Alright, bye. This one becomes 1 over s squared. Whereas the Laplace transform acting on the constant 1 is going to be equal to 1 over s. and here's what we can do. Here's the reason this is useful. It's because it's a linear function and we can Laplace transform the entire equation and then we undo the Laplace transform after we solve the equation. But first we have to figure out what y here is first though. Because I actually also forgot about how to find the Laplace transform of a function f prime. Laplace transform of f prime, if I remember correctly, which I could be incorrect, I think it's going to be equal to s times f prime naught plus f naught? I don't remember that well. Let me check. Of derivative. Yeah, Laplace transform of the derivative is equal to Laplace transform of the derivative is equal to, yeah, okay. I was almost right. This was actually supposed to be, well, not really almost right. It was close enough, chat, close enough. Don't clown on me. It's going to be s times the Laplace transform of f minus the initial condition for f. Okay. The fucking Laplace? Yeah, I'm solving the Laplace transform. Actually, hold on. Wait, my chat isn't showing. Chat filter all messages, please. Yes, we're doing the Laplace transform here today. My phone is very much dying. Yeah, there we go. We're back. Top messages, show all messages, and yeah, the Laplace transform. Chat, yes. What is it? So if we use the Laplace transform on f double prime, it's going to be equal to s times the Laplace transform of f prime meow. True. True. That's fair. Laplace transform. This will be. I'm going to be very thankful for these initial conditions that they gave us. So the Laplace transform for the second order derivative is going to be equal to that, equals to s, and then this is going to be Laplace transform of s of f prime there. This is going to turn into s times the s Laplace of f prime, no, Laplace of just f, and then subtracted by f of f at 0, and then subtracted by f prime at 0. In general, which means in general, the nth derivative here of the Laplace transform of the nth derivative of a function is going to be equal to s to the n times the Laplace transform of the original function times the Laplace transform of the original function subtracted by it's subtraction. It is subtraction. It's going to be subtracted by s to the power of n minus 1 times the f to the n minus 1. The initial condition at s to the n minus 1. And then you add all of that, so it becomes s to the n minus 2, f n minus 2, 0, subtracted by s to the n minus 3, f to the n minus 3, 0, dot dot dot, etc. Unless I did that wrong. I in fact did that wrong. Fuck. This is f1. This is the first derivative. This is going to be the second one. There's the second one, and then there's going to be the third derivative. It's actually backwards. I put it on backwards. Okay. So that means, so for example, in our instance, we had L Laplace transform of f to the 2, the second derivative of f, which is going to be equal to s squared, the Laplace transform of the original function, subtracted by s times the first derivative of the function, and then subtracted by f of the original function, which is not correct. This, I'm stupid. I'm wrong again. This f1. This is going to be f1. This is going to be f2. This one's going to be f itself. This is going to be the first derivative of f. This is going to be the second derivative of f. There we go. Okay. Yeah, because the prime is supposed to be over here, not over there. Alright, cool. So now that we have this, we're gonna write out the Laplace transform for all of them. So there's gonna be f of the fourth derivative of f is gonna be s to the 4 L f minus s f0 minus s squared f prime 0 minus s cubed f double prime 0. And I did it wrong again because I'm stupid. 3 is supposed to be there. This is supposed to be s to the power of 1. Why did none of you guys warn me, chat? None of you guys warned me. I've been streaming for 3 hours. Well, you know what? It's worth it for the silksong. Okay, and that's the Laplace transform formulas that we are gonna keep in mind. And I'm gonna move and I'm gonna move it all. Nope, and I'm gonna move it all the way over here. Yay! So now we Laplace transform the entire equation. Silksong tomorrow. Yeah, silksong tomorrow. Let's go. We Laplace transform the entire equation. We're gonna get s to the power of 4. Y. What should I call it? I'm not gonna call the Laplace transform just Ly. I'm gonna call it big Y. Okay. I'm gonna call it big Y because why not, right? And this is gonna be subtracted by s cubed times y, I think that just y, right? Yeah, y at 0, which conveniently is equal to 0. So that means, in our case, y quadruple prime, the Laplace transform of y quadruple prime, is equal to that, it's equal to subtracted by s to the power of 2 y primed subtracted by s to the power of 1 y double primed subtracted by y triple prime at 0. Okay, and then we set, and then it's going to be equal to what? What do we have? It's equal to s tesseracted y. This is going to be y. So this term is going to be 0. This term is going to be 0. It's going to be s to the power 4 minus s, because y double prime is 1, and minus this one, so it's going to be minus 1. So now we do that to L y double prime. Okay, we do that to 2 tesseracted. Yeah, I just said tesseracted for cubing the equation. I think the stream delay is getting a little ridiculous. Not sure what the hell happened, but I think the stream delay is kind of crazy right now. It's going to be equal to 2s squared big Y subtracted by 2 normal s, and then just y primed. No, just y, not y primed. And then it's going to be subtracted by 2 times y primed 0, which is going to be equal to 2s squared y subtracted by 2s, because y 0. Oh no, we can cancel all of these out. Okay, I thought, okay, yeah, I can do that. So let's just go ahead and do it. I'm so excited, because we don't have to deal with as many terms. Okay, and then of course we Laplace transform the normal y. Is going to be equal to, you know, just y. And then on the other side, it becomes, so what we have is we're going to have the Laplace transformed equation, which is s to the power 4y subtracted by s subtracted by 1 plus 2s squared y plus big Y is equal to 3 over t squared, 3 over s squared plus 4 over s. This is because we applied the Laplace transform on this term. Laplace transform on t is going to become 1 over s squared, and we multiply that by 3. This term 4 we multiply it's just 1 times 4, so it becomes 4 over s. Okay, and now we solve the equations. So we can pull out y there, and then the rest is going to be equal to s to the power 4 minus, no, plus 2s squared plus 1. I know the answer to that, I think. Yeah, I think, okay, and then that becomes 3 over s squared plus 4 over s plus s plus 1. In this case, I'm going to turn this into something divided by 1, something divided by s squared. So that becomes 3 plus 4s plus normal s plus plus s squared, because because this term, no, that's going to be s cubed plus s cubed plus 1, so that's going to be plus s squared, and dividing both of that, all of that, by s squared. So we're going to be getting s cubed plus s squared plus 4s plus 3 divided by s squared. Here we have y equals to that, which means, well, we can set y, and this is actually going to be equal to s squared plus 1 squared. I think that's right. That's going to be s, and the right hand side is just going to be copy pasted. So y is going to be equal to s cubed plus s squared plus 4s plus 3 over s squared plus 1 squared. And yeah, okay. And now we're going to have to find y. We have to find the original y function by applying the inverse Laplace transform. But we can't do that right now because we are kind of stuck with this big ass terms. So what I can do, what I'm going to do is I'm going to use partial fraction decomposition. That is, this is going to be equal to big A over S plus big B over S squared plus big C over S squared plus 1 plus big D over S squared plus 1 squared. And we're going to have to solve to find A, B, C, and D. And then we're going to apply the inverse Laplace transform. Inverse Laplace transform, which has its own table, which we can look up. Yeah, can I open this image? Is it going to be big? It is going to be big, okay. Yeah, we can look up using this. Here you can see that eventually we'll probably get something like this term. We'll probably end up with this term or something similar. And then we're also going to end up with this term. We're going to end up with this term as well. So it's going to be some polynomial and shit. So what I'm saying is there will still be long ass terms, but it's going to be less painful than what we did. All right, so let's go ahead and do that. Oh shit. It's still a lot, but I think it's considerably less than what we just had. Yeah, I'm not going back to that shit. B is going to be multiplied by s to the power 4 plus 2s plus 1. This this term is going to be c times s squared, and then s squared plus 1. And then this term is going to be ds squared. Are we supposed to be seeing this? You guys can see it. I'm still streaming for a reason, I guess. And it's going to be equal to s squared plus 1. All right. And it's going to be kind of big, but it shouldn't be too big. Shouldn't be too big of a problem. Hold the table, I mean. Oh shit! I forgot. I was okay. I just rewrote the whole thing. All right. You guys didn't miss. You guys didn't miss much. Don't worry. Okay. So here, what do we have here? We can instantly. You're gonna stream until silksong releases and stream it? No, that is gonna be like tomorrow. And by tomorrow, I mean like in 23 hours. Exactly 23 hours, in fact. I'm gonna tweet that out, actually. Woo, silksong in 23 hours. Silksong in 23 hours. Alright. Okay, I'm back. Yeah, unfortunately I'm not going to be streaming silksong because I don't think my computer can handle it. Because right now it's barely handling my stream, even though it's just paint.net. Granted, it's paint.net. This one becomes... We can kind of just roll out A to be 0. Because... Unless I did something wrong, this becomes as... This is... Yeah, we can roll out A to be 0. Because over here on the left hand side we will have s to the power 3. Over here, A here is going to combine into s to the power 5. And that's the only thing that A has. So therefore A should be 0. Fortunately. A is going to be 0. A is 0. But we still have to deal with the rest. We'll be fine though. We still have to deal with the rest. That is, we're going to have B plus C equal to 0. Because B here, B multiply B with s to the power 4. C s squared times s squared is C s to the power 4. But there's no s to the power 4 term here. So that's one equation that we got. Next up, let's look at s to the power 3. What? Oh, okay. Okay. Give me a second, guys. I completely forgot about how to do partial fractions. Okay. Here's what's gonna happen. Here's what happens. The actual way to do partial fractions is to there's going to be bs plus 1. No, bs plus c divided by s squared. This is going to be ds plus c over s squared plus 1. This, plus e. F s to the power of 3. Oh god. Plus A, B, C, D, E, F, G, H, I, okay, and then that's gonna be it. So really, we're dealing with a fraction. We're dealing with a few more variables than we thought. Oh god. You know what? My dinner can wait. Streamer forgets ABC. Oh my god, I'm gonna get clowned on forever for that. Okay, well, let's do this. This term becomes A times S times S to the power 4 plus 2S squared plus 1. This B term is going to be multiplied by that, so it's going to be BS times S to the power 4 plus 2S squared plus 1. Oh wait, which means that this guy and these two guys get absorbed into one another, like as in like we can kind of just change this. Okay, hold on. I can just remove this. Yeah, give me a sec. I can remove this term because if we find A, it's gonna be part of B anyways. How could I have forgotten? So yay, less terms to deal with. But we went from 4 to 8 variables. Not ideal, still. Not ideal. I prefer not dealing with this many variables. But well, we're here, so C times S to the 4 plus 2S squared plus 1. Hello, Cookie, right? Hello, welcome to the stream. Welcome, John. Welcome to the stream. Yeah, welcome to the stream. How's your day going? This is S cubed. This is no, this is the S, and then that's the S squared, and then S squared plus 1. Yippers, hi. Just fine, thanks. Nice. I'm doing not very well because of this goddamn question. Because I have to calculate for a few too many terms. That's gonna be S times S squared. That's gonna be S cubed plus S. And that's not all. We still have that thing to deal with. As you can see, Laplace equation, Laplace transform gave us this, but like even if we did any other way, it would have been equally bad. So this is kind of inevitable. This s to the power 5, but at least Laplace transform eliminated the problem with the boundary conditions right away. It dealt with it right away. So I'm kind of glad that happened. Plus I s squared. And all of that divided by s squared plus s squared times s squared plus 1 squared. Okay, yeah, I think that's right. And it must be equal to s cubed plus s squared plus 4s plus 3. So let's take a look at what we got. First of all, we immediately know that c is equal to 3 because c is the only one with the without the squared term. So yeah, c is the only one without s. So c equals to 3. We know that right away. Good. Next up, it's going to be a little more complicated the further we go, but we'll be alright. We also know that b plus e, bs time, multiplied by 1 here is going to become bs. This es, so b plus e is equal to whatever is multiplying by s right now, which is going to be 4. Also, why is their variable b to I? Welcome to ordinary differential equations. I hate this a lot. And you probably hate it too, don't worry. Hold up, do we even have enough equations? I don't think we have enough equations, but I think I'll figure it out as I go. It'll probably make sense at the end. I love streamers suffering. Help. Okay, so this is S4. What else? What else can I? Let's see. S squared. What do we have for s squared? S squared is 2c plus d plus I equals to 1. And then s cubed is going to be 2b 2b2t? No, okay. The oldest unlucky server in Minecraft. Plus h is going to be equal to 1. And then bs s to the power 4. We have c s to the power 4 plus d. That's s to the power 4 plus g is equal to 0. And then s to the power 5 is b plus any more? Oh, b plus f is equal to 0 as well. And I think that's all the terms. Yeah, I think we've taken care of all the terms. So now we have how many equations? 1, 2, 3, 4, 5, 6. And how many variables do we have? B, C, D, E, F, G, H. What the fuck? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 equations, and for some reason we only have 8 equations, but no, we have 8 unknowns and 6 equations. I think I may have done something wrong here. Actually, no. You know what? I think it's because I used this. These two got duplicated. So I remember that we have to do this. but like maybe we don't. Maybe actually we don't. Let's see. If I multiply this, it's gonna merge into these terms. Yeah. So D and E doesn't really matter here. So I should just delete D and E, which is gonna help us because it's gonna reduce the number of variables to deal with. Okay, and the rest is gonna be pretty easy now. I'm gonna verify that in the end as well, either way, but like, so now we know that I is equal to -5, G is equal to -1, -3, G equals -3, wait, what? 1, 2, 3, 4, 5, 6. 6 equations. 1, 2, 3, 4, 5, 6. 6 unknowns. Okay, so 2b plus h equals to 1. B plus E equals to 4. B plus F equals 0. C equals to 3. I equals to -5. And G equals to -3. Okay, I see what it I see what it is. I see how it is. So we're still missing one equation. Did I chat? I may have fucked something up. What did I do wrong? Wait. Yeah, those are 6 variables. Wait. Oh, where the fuck did E come from? I already deleted it. Bruh. Okay. So we now know that B equals to 4. Therefore, H equals to B equals to 4. H is going to be equal to -7, right? -7, yeah. And then F is equal to -4. And now we have that. So Y is going to be equal to, big Y is equal to 4s plus 3. 4s plus 3 divided by s squared. No, that delete that. And then plus -4s cubed minus 3 gs squared minus 7s minus 5, and all of that divided by s squared plus 1 altogether squared. Okay. Stream adventure. What's the question? The question is this one. We have to solve this differential equation, and there are many ways you can solve this equation, all of which are painful because you have to deal with at least 6 variables. I decided to use the one we haven't learned, but yeah, I'm having fun. Okay. So now we have to do the inverse of Laplace transform, which there isn't a specific way to do. C. Why did I write that as C? There's 3. We already solved this. This one becomes minus 4s cubed over s squared plus 1 squared, which we should be able to use the table to figure out. Yeah, I think we'll be able to figure it out with that. Although I don't... Is there a better way to look at this? Or is that just... Yeah, okay, fine. Okay. Alright, and then that's gonna be minus 3. But that's not G anymore. I already set it in. I may actually have dementia, chat. What the fuck? How long has it been since I started the stream? S squared plus 1 squared. There's minus 5. S squared minus 1. No, S squared plus 1 squared. Okay. Now let's look at the table and see what you can do. Cos AT is that. Do we even have that term? We don't have that term. We need to find a term that's like oh yeah, okay, so this term is what we're gonna need. No, these terms are gonna be what we're gonna need. Alright. We do go up to S cubed. Okay. So let's see. We're gonna try to format it in that way. So let me come back here. And we're gonna format it in that way. That is, we're gonna find a way to format it such that we know that S times S squared plus 3A squared what are Laplace transformations? Basically, Laplace transformation is a way to solve a differential equation by applying a linear transformation across the entire equation, and then you solve it, and then you undo the Laplace transformation. Okay, we have to find a way to make it in that form. So I'm gonna use this guy as our victim. 4 over S, there's gonna be 3S squared, there's gonna be minus 4. And that's gonna be S multiplied S squared plus 3A. In our case, A is 1, so this should be plus 3. And then this, and then we're gonna subtract it by 3S, so that it would still be the same. And this one is gonna be minus 3. It's gonna be minus 3S squared, which has this form, so we can solve that with that. Anything else that we can do? Is there any other form that we can use? That's S squared, yeah, that's just S squared. I'm panicking a little bit because we don't have this term. We don't have like a term without the S, with just the S. Is there? No, I don't see it right now. Chat, we might be cooked. Let's see. You know what? Whatever happens, happens. There we go. Oops. Okay. There's gonna be S over S squared plus 1 squared, which follows that form. Actually, no, it doesn't. It's gonna be 2, and that's gonna be 1.5. So that's gonna become 3 over 2. And then we will have this S term. You know what? I'm gonna pray that this S term and this term cancel out. So we're gonna have minus 7 S minus 5 over S squared plus 1 squared. Okay, so what we have is gonna be 4 over S, 3 over S squared, subtracted by 4, And then we have s times s squared plus 3 over s squared plus 1 squared. This is going to be added by 12s over s squared plus 1 squared. This term is going to be 3 over 2s squared over s squared plus 1 squared, subtracted by 7s minus 5 over s squared plus 1 squared. That's okay. The 7 is up here. Sorry. The 7 is up there. And then we can add that actually. Wait, yeah. And then we can bring this thing in and merge with that. This is actually going to be plus 5. So that's going to be merged together. And we're going to have 4. We just copy the whole thing again. We copy the whole thing again. We remove this because this is 12s. This is minus. So this is going to be. So this is going to be minus. There's going to be minus 12s, which is going to merge with that one to become minus 5. Minus 5. And then we can just erase this guy completely. Boop. Okay. And now we can solve the remaining bit. Let me see. Does this format fit anything? Oh, there it is. There it is. 2as is equal to 2as divided by s squared. Yeah. Okay. So there's a way to answer that. All right. Cool. So that's going to be equal to again, copy the whole thing. Copy the entire thing. Please don't get bored yet, guys. I'm not bored yet. You guys shouldn't be bored yet. So this term is going to be replaced by just so this whole term is going to become plus 5 minus 5. Honk me. No, don't go. Stay with me. Don't leave me here. S over s plus s squared plus 1 squared, and then this minus 5 1 over s squared plus 1 squared. Is that right? This one, me such confused human hairs on the other side of my face. Bruh. Okay, so this one becomes 5 over 2. This becomes 2s. So that it would line up with the Laplace, with the formula. Because here a is 1, so that should be 2 as well. This is going to become 2. There's going to be 5 over 2. And now we can do it. This is y, so therefore now we can undo the Laplace transformation. Y equals to the inverse of the Laplace transformation of big Y is equal to, okay, so 4 over s. If we undo that, what do we get? What we're going to get is we're going to get we're going to get 4 times e to the power of, no, wait. Okay, wait. This is 4 over s. So this is going to be 4 times the inverse of 1 over s. So this is going to be just 4. Equals to 4. This one is going to become 3t, I think. Because this is n factorial is, yeah, and n here's 1 because there's s to the power of 2. So it's going to be s to the power of 2, and this n here is 1. So it's going to be 1 over s squared is equal to t. It gets transformed to t. Therefore, this becomes 3t. Then, oh boy, this is gonna be s squared plus 1 here is gonna be corresponding to this term. Where is the term? It's gonna correspond to that term, s squared plus 3a squared. Yeah, so there's gonna be minus 4 times that term, which is gonna be cos at plus at sine at. Cos at, t is 1, a is 1, plus at, no, plus at sine at. Right? At sine 1. So that would be t sine 1. T sine t. So that's this term. Next term is going to be minus 3 over 2. Minus 3 over 2. And 3 over 2, that's going to be 2s squared, which is going to correspond to this one, which is going to be sine t plus t cos t. And then we have this remaining term, which is going to be 5 over 2. This one is going to be 2s. So 2s here is going to be equivalent to this one. So it's going to be equal to t times sine at. T sine at is going to be t times sine of a is 1. So it's going to be t sine t. And this last term is going to be 5 over 2. 2 is going to be cos, I think. This one is going to be sine at minus at cos at. So sine t minus t cos t. Boop, boop. And so now we have our answer. Let me just plug in the, let me just make it easier to read. So it's going to be 4 plus 3t minus, this is mildly threatening, but this is going to be 4 cos t. Let me collect the like terms for sine real quick. There's going to be minus 3 over 2, okay. Minus, so this is going to be minus 3 over 2 sine t, and then minus 5 over 2 sine t, so it's going to be minus 4 sine t. This next up is the t sine t terms, I think. Yeah, let's deal with t sine t terms first. So it's going to be minus 4 t sine t plus 5 over 2 t sine t. So it's going to be minus 3 over 2 t sine t. And then we also have minus 3 over 2 t cos t plus 5 over 2 t cos t, which is going to be plus t cos t. And how you get there? Oh my god, I'm a bad answer. This is the Laplace transform. Basically, I use this table, which normally you wouldn't memorize the whole thing, but this is the this is the Laplace transform. It's magic. You know. You know, classic ecstatic. It's magic. Anyone got that reference? I hope someone got that reference in chat. There's gotta be there's 5 people in chat. Someone's got that. I honestly can't remember the rest, the lyrics out loud. Anyway, well, that's our answer. Y equals to that. So let's see. Let's prove that by plugging it in. I'll need to study this thing. I bet comp sci probably has. It might have, because computer science, you might get to solve ordinary differential equations. Let me see. 4 plus 3x. I'm going to turn x to t. So minus 4 cos x plus, no, minus 4 sine x minus 3t minus 3 over 2 x sine x minus, no, was it plus 1? No, x cos x. Yeah, it's plus x cos x. All right. Actually, what was the lyrics after that? I don't know. It's like the one line in the chorus that I genuinely can't remember. But let's see. Let's take the first derivative of this function. I'm going to call this function f of x. And the first derivative of the function at 0 is 0, which is what we expected. If it's the second derivative, it should be 1, as expected. If it's the third derivative, it should also be 1. Fourth derivative doesn't really matter. But, alright, so that's that. Now, let's see if the differential equation is correct. The differential equation is y, the fourth derivative of y plus 2f double prime x plus f of x. Well, that looks sane. That looks sane, kind of. And let's see if that's true. And we compare this to 3x plus 4. And it lines up perfectly. Which means we got this answer. We got this correct. We got this right. Ooh, boy, that was crazy. I haven't had any dinner yet. Fun fact. Alright, I'm gonna save this real quick. No more suffering. Yeah, we can go now. And then tomorrow... Oh, sine wave, yeah. Until you get more homework. True. But tomorrow is silksong, baby! Let's go! I'm probably not gonna stream it because my computer can't handle it, as I said earlier. But yeah. Silksong tomorrow, I'll most likely be playing it. So you guys can have fun, have a great day for, yeah, I have to go eat. Yeah, have a great day. See you guys. You know what, I'm gonna save this. I'm gonna save this one. Normally I just don't, but like in this case I feel like I should. Q1DE. Yeah, okay. Boop, saved. Okay, and the rest, these classical mechanics problems are kind of easy. The calculus problem was kind of okay. And then we have this tedious part that is differential equations, which is a mistake. I should not have. Why would I do this? Anyway, well, have a great day. If you guys haven't watched it already, go watch my video on spatial relativity. Please. I re-uploaded it, so the audio quality, I think the audio is better now. So you guys can go watch it and tell me what you think. You should watch it again if you already watched it. Yeah, because I want views. When is the next class? Tomorrow. Wait, unless you mean like next stream. Oh, by next stream, I don't know. It depends on when my teacher give me the homework. Give me more homework. Which is not right now, so I'm gonna relish that and play silksong tomorrow. Alright, gonna end the stream now, so hope you guys have fun. Or like at least just have something to listen to while you guys do your own thing. So yeah, thank you for watching. And actually, wait. I want to show you guys something first. There's this little graph that I did. Actually, you know what? I'm gonna tease it for next stream. I'm not gonna show it to you guys yet. So if you guys want to see it, you guys better tune in for the next stream. Because I am in fact getting a little hungry. Okay, so see you guys next stream or next video if I somehow upload the video first. All right, bye bye.